Computer Organization and Architecture. Chapter 3. System Buses. The von Neumann architecture is used in the construction of modern computers. This architecture has three main concepts. Data and instructions are stored in memory that can be read or written to. Memory locations are addressable regardless of data type. Execution is sequential, from one instruction to the next, unless the instruction sequence is modified to be complex unless it's complex. A component that performs processes according to von Neumann's ideas must consist of the control unit and arithmetic logic unit, ALU, located in the central processing unit. Data and instructions required for the system and the resulting output. Temporary storage for the code and results of processing, such as main memory. So the component base on there are memory stores both data and instructions that will be retrieved or stored by the central processing unit, or CPU, I/O module for transfer data in and out, and buffer to store data in I/O module. The top-level view of computer components is shown that memory stores both data and instructions that will be accessed or stored by the central processing unit, CPU. The CPU has components used to exchange data with memory, including registers, temporary data storage, as follows. PC, program counter, is a counter register that stores the address of the next instruction that the CPU will execute. IR, instruction register, is an instruction register that stores the instruction that has been fetched for processing. MAR, memory address register, is a register for storing memory addresses. It stores the memory address to be read or read to next. MBR, memory buffer register, is a buffer register that stores data for temporary memory. It stores the data to be written to. IO, address register, IOAR, is a register used to specify the address of an input-output device. Its function is to specify the address of an input-output device, IO device. IO buffer register, IO buffer register, is a buffer register used to temporarily store data for input-output devices. It is used for exchanging data between the input-output module, IO module, and the central processing unit, CPU. 3. The input-output module, IO module, transfers data from external devices to/from the CPU and memory, and from within the IO module. It has an internal buffer that stores temporary data to be sent temporarily. 4. A buffer is a temporary storage location for data, using timing, because the CPU and the I/O module are not synchronized due to the device being slower than the CPU, or to prevent data from being overwritten when a device sends data while the CPU is not busy. The instruction cycle. At the start of the instruction cycle, the number in the counter register, or PC, represents the memory address from which the central processing unit, CPU, needs to read the instruction. This address is then stored in the instruction register, IR. When reading an instruction, this address is sent via the address bus to the memory outside the CPU. The control unit simultaneously sends other necessary signals to the memory. The memory then sends the data at that address back via the data bus, stores it in the instruction register, and then decodes and executes the instruction. Command working steps can be divided into two main steps as follows. Fetch cycle is the process of fetching commands, enters the central processing unit to wait for processing. Execution, execute cycle, is a processing step. The fetch cycle has the following steps. Central processing unit. Want to fetch the next instruction from memory pointed to by PC. The value on PC is increased by 1, which points to the next instruction. Instruction will be loaded into IR. The central processing unit will interpret instruction and cause the process to work, action, according to that instruction. The execution cycle generates actions that can be interpreted and divided into 4 categories. Processor to from memory. Data is transferred between the processor and memory. Processor to from I/O. Data is transferred between the processor and I/O. Data processing. Calculations and comparisons are performed on the data. Control. Jumping sequences to execute other instructions. And combination of any executions. This illustrates is a partial program execution, showing the relevant portions of memory and processor registers. The program fragment shown adds the contents of the memory word at address 940 to the contents of the memory word at address 941 and stores the result in the latter location. 3 instructions, which can be described as 3 fetch and 3 execute cycles, are required. 1. The PC contains 300, the address of the first instruction. This instruction, the value 1940 in hexadecimal, is loaded into the instruction register IR, and the PC is incremented. Note that this process involves the use of a memory address register and a memory buffer register. For simplicity, these intermediate registers are ignored. 2. The first 4 bits, first hexadecimal digit, indicate that the AC is to be loaded. The remaining 12 bits, 3 hexadecimal digits, specify the address 940 from which data are to be loaded. 3. The next instruction, 5941, is fetched from location 301, and the PC is incremented. 4. The old contents of the AC and the contents of location 941 are added, and the result is stored in the AC. 5. The next instruction, 2941, is fetched from location 303, and the PC is incremented. 6. The contents of the AC are stored in location 941. In this example, 3 instruction cycles, each consisting of a fetch cycle and an execute cycle, are needed to add the contents of location 940 to the contents of 941. With a more complex set of instructions, fewer cycles would be needed. Some older processors, for example, included instructions that contain more than one memory address. Thus, the execution cycle for a particular instruction on such processors could involve more than one reference to memory. Also, instead of memory references, an instruction may specify an I/O operation. The execution cycle for a particular instruction may involve more than one reference to memory. Also, instead of memory references, an instruction may specify an I/O operation. For any given instruction cycle, some states may be null and others may be visited more than once. The states can be described as follows. Instruction address calculation, IAC. Determine the address of the next instruction to be executed. Usually, this involves adding a fixed number to the address of the previous instruction. For example, if each instruction is 16 bits long and memory is organized into 16-bit words, then add 1 to the previous address. If instead memory is organized as individually addressable 8-bit bytes, then add 2 to the previous address. Instruction fetch, IF. Read instruction from its memory location into the processor. Instruction operation decoding, IOD. Analyze instruction to determine type of operation to be performed and operand or operands to be used. Operand address calculation, OAC. If the operation involves reference to an operand in memory or available via I/O, then determine the address of the operand. Operand fetch, OF. Fetch the operand from memory or read it in from I/O. Data operation, DO. Perform the operation indicated in the instruction. Operand store, OS. Write the result into memory or out to I/O. States in the upper part of Figure 3.6 involve an exchange between the processor and either memory or an I/O module. States in the lower part of the diagram involve only internal processor operations. The OAC state appears twice because an instruction may involve a read, a write, or both. However, the action performed during that state is fundamentally the same in both cases, and so only a single state identifier is needed. Also note that the diagram allows for multiple operands and multiple results, because some instructions on some machines require this. For example, the PDP-11 instruction add A, B results in the following sequence of states: IAC, IF, IOD, OAC, OF, OAC, OF, DO, OAC, OS. Finally, on some machines, a single instruction can specify an operation to be performed on a vector, one-dimensional array of numbers, or a string, one-dimensional array of characters. The instruction cycle indicates this would involve repetitive operand fetch and or store operations. In real-world computer applications, computers need to control and respond to external signals, whether from output devices or other sources. While a computer is running, if an external device requests access to the central processing unit, CPU, causing the CPU to pause its current program and execute the interrupted task, this interruption occurs. The task requested by the computer is usually a pre-prepared program providing a crucial service. This is called an interrupt service routine. Examples of interruptions include notifying the computer that an input device has finished processing or that an error has occurred. An interrupt is a method by which another unit or module, such as I/O or memory, or an error notification during system operation, needs to temporarily halt the central processing unit, CPU, to execute the interrupted task. Once the interrupted task is completed, the CPU's regular task that was interrupted is resumed. Tasks that cause interrupts can fall into 4 groups. Program tasks. These arise from program conditions or abnormalities in program execution, such as calculation overflows, division by zero, unknown instructions, incorrect code generation, or unavailable memory access. 2. Timers. These are generated by setting a time limit for the CPU to execute an interrupt, or by creating a signal to interrupt the CPU so it can jump into the operating system to perform regular basic tasks. This includes maintaining and updating timers and setting interrupt times to monitor tasks awaiting execution. 3. Input-output, I/O tasks. These involve generating timing signals from the input-output controller to inform the operating system that an input-output operation has been completed or to retrieve values from a buffer. For example, when reading input from the keyboard, the CPU jumps to the operating system to retrieve the data. Or when writing data to the screen, it interrupts the system to inform the operating system that data has been retrieved from the buffer. 4. Hardware failure occurs due to a malfunction, such as a power outage or errors in the parity sensor used to check data. In a computer system, every component must be interconnected to perform various types of operations, including memory connection, input-output device connection, central processing unit, CPU connection. Memory connection refers to the connection for receiving/sending data, receiving addresses, and receiving control signals, such as read signals, write signals, and timing signals. Input-output connection. This connection is used for output, by receiving data from the computer and sending data to external devices. Input, by receiving data from external devices and sending data to the computer. Receiving control signals from the computer. Sending control signals to external devices, such as spinning a disk. Receiving address information from external devices, such as the port number used to identify that external device. Sending interrupt signals. The connection to the central processing unit, CPU, is for reading instructions and data, saving results, sending control signals to other units, and receiving interrupt signals. A bus is a pathway for connection within a system, between different devices. There are a number of possible interconnection systems. It might be single and multiple bus structures are most common. The multiple bus, for example, control, address, data bus in personal computer or PC. The single bus, for example, unibus in DEC, PDP computer.